All right, so we've worked our way through Newton-Euler equations. We're able to derive a system of equations, describe our rigid body dynamics. And at this point, I want to take a quick segue into discussing what we do once we have the equations. Now, in general, we've got, and again, I'm pulling from the notes that are on that evaluating equations of motion section. In general, we have, so we're asking ourselves how to evaluate our equations of motion. In general, we're presented with In general, we have, I'm listing three approaches. The first approach would be look for a closed form solution. And our equations, recall, are second order differential equations. Well, here I need to say they're second order ordinary differential equations. They're ordinary differential equations because we're assuming rigid body. Our differentials are in time only. They become partial differential equations if we start to consider elastic deformation, which we could do, but at the moment the problems are complicated enough. We know that we can get closed form solutions to special classes of those problems, and those classes are in cases where they're linear. So if the equations are linear, then we should be able to get linear equations, and we should be able to solve in closed form. I don't have the notes from last time. I'm wondering if I can jump to another lecture though and just look at an example. Yeah, here we go. Here is the example. This is now about 2 lectures back. We did work an example here. So let's look at these equations of motion. In this case, we had this rotating shaft with a eccentric, some mass located off, and we worked the problem. We worked out this problem together, and we worked our way down to the bottom, and it looked like this was our, here we go. Here are our equations of motion written in matrix form. I'm going to scroll back up. Here are our equations. Here was the first time we wrote our equations. So we said M1, M2, M3 equals these terms. Here we wrote them in the body fixed frame. And here we wrote them in the inertial frame. And then once again, we cast them in this matrix form. So here are our equations of motion. Now, first of all, we've got a couple of complicating factors, actually. Recall, we're looking for cases of closed form. Can I solve these in closed form? Well, I've got two complicating factors, potentially. One complicating factor is that my unknowns are not only differential, but they're also algebraic. So that implies that this system is a system of differential algebraic equations. And the closed form solution that we have so far, we've not considered this case, so that would make it not this case. Now, actually, this one is somewhat simplified. It looks like this theta double dot is explicitly known. It looks like the other two terms are not coupled here. So this looks like a reduced problem where perhaps we could get this guy reduced in terms. The second problem that we have, I can see, and let's just look at the second term, is if our terms, here I have a coefficient, but it's a function of theta. So this cosine of theta, over here I have a sine of theta. These things tell me that my equations are nonlinear. Those are nonlinear terms. Anywhere we have a sine and a cosine. And I think that's almost always going to happen. So in the first case, linear equations, but we have to recall in almost every case that we will run into, we're going to have nonlinearities. We're going to have nonlinear equations, again, because of the trigonometric functions. Really, the rotation will call into play. The second scenario we can look at would be numerical solutions. Actually, I should jump back. There are probably some closed form solutions, very sporadic closed form solutions to special cases of nonlinear problems. But those are rare. I'm going to assume that they don't even exist for our purposes. The second case would be numerical solutions. We use MATLAB or any other numerical solver. And this, in my mind, is going to be the primary workhorse of solving more involved problems. And if you're trying to do simulation or analysis in many cases, and we will spend some time looking at that. Numerical solution, this could treat any problem. I mean, we're not really limited. We're not limited to the type of problem we can solve. Of course, the downside is it is numerical, which means that I'm going to be solving these problems using traditional numerical solution techniques, and all those numerical solution techniques will assume a form. They'll assume a solution and apply it repetitively. The solution is quite accurate, but there are always those higher order terms. Those higher order terms, depending on the nature of the problem, could be something that effectively stay in the noise region, don't impact your problem, or those higher order terms could show up and cause problems. So that's the one thing we have to be aware of. We'll spend some time looking at numerical solutions. And then there's a third technique that we're going to talk about today, will be called phase portraits. And phase portraits can work for linear and nonlinear problems. Not all, but quite a few. And they avoid the problem of having to solve the differential equation, in a closed form technique. That's the pro. The con is that they work for 1 degree of freedom only. Okay. But it's a useful tool. So here are 3 methods. I'm sure there's more. We will spend time later on this guy, but today I want to review closed form solutions just for when they exist, and then I want to review phase portraits. So first, let us consider the closed form solution. And frankly, this is a review, so I'll go through it kind of quickly. And generally speaking, when we solve these, I always just refer to my favorite reference to go through that, but it's worthwhile spending a little bit of time talking about it. And we're going to look at a subcase. So we're looking at closed form solution to second order differential equation. It's going to be an ODE. And the special case, we're going to consider our constant coefficients and a homogeneous solution. Homogeneous case solution. So an example would be, and I'm going to come up with a very simplistic dynamic example. So I've got a mass spring system. I could throw a damper in there. This is my mass, some m, it's moving with x, and we know this gives us, it's a one-DOF case, gives us a solution mx double dot plus cx dot plus kx equals 0. It's homogeneous, these are constant, and you can see it's linear. All the unknowns, the parameter x is to the first order, not contained in sines and cosines. So in general, the approach is to assume a solution of the form and as a quick aside, assume a solution of the form x equals a e to the lambda t. Call call it R. I'll follow our notes. I always think to myself, assume a solution. So I can assume any kind of solution. Well, have you ever seen anyone assume a solution other than that? I don't know why they don't say some very brave and intelligent person figured it out, and from now on, we all copy that person. But no, we don't say that. We say assume a solution. Anyhow, we assume the solution. It turns out that it does work. Then if we take the time derivative of that, x dot equals a r e to the rt. And x double dot is the next derivative. Oh, by the way, here, of course, a is a constant, t is time. Second derivative is ar squared e to the rt. And by choosing this solution, I can go back and plug it in to my equation. So I get m a r squared. I think I can pull out the a. So I get mr squared plus cr plus, this should have been an x up here, k times a e to the rt equals 0. And this guy is my characteristic polynomial. That I'm going to use to solve for r. I know in this solution, either this guy has to equal 0, this guy has to equal 0. Well, I don't want this guy to equal 0. That's my assumed solution. So that means that my characteristic for this equation to hold, my characteristic polynomial must equal 0. So I get mr squared plus cr plus k has to equal 0. And so I have to solve this for r. And when I solve for r, note that I'm going to get 3 cases. Well, I guess we break it down in 3 cases. I guess right off the bat, there'd be 2 cases. Either r is going to be real or it's going to be complex. Or you could say it's going to be complex with either 0 or non-zero imaginary values. The third case will be the possibility that r has real and repeated roots, okay? So we'll look at those. So our 3 cases are, first, r has 2 roots, and they are real and the same. So we'll just say r equals r1. And in that case, when we plug it back in, our x, okay, by the way, we plug it back in with our initial conditions, and our solution then becomes a1 e to the r1t plus a2 time e to the r1t. And again, a1, a2 come from the initial conditions to the problem. I didn't state the initial conditions, but let's review. What would be the ICs up here? The ICs would be the value of x at time 0 and the value of x dot at time 0. I would need that to solve this time-based problem. The second case is, again, 2 roots, both real, and not equal, and different. Or not the same. I guess the same would be a special case. So r is r1 and r2. So in this case, x is a1 e to the r1t plus a2 e to the r2t. And again, a1 and a2 come from initial conditions. In the third case, r has 2 roots. I guess r always has 2 roots. I don't know why I say that. They're complex. So I'll just say the 2 roots are complex. And not complex as in complicated, but complex as in containing real and imaginary parts. And so r is going to equal. We can write them different ways. For some reason, I'm here using alpha and omega. So r1 is alpha plus omega I and alpha minus omega I, with I, the imaginary operator, or I is the square root of -1. And then our solution becomes x is a1. So I just plug in my roots here, e to the alpha plus omega I t plus a2 e to the alpha minus omega I t. Now I can, now this is the, this would be just the way of plugging it in, but this is not the way we write the solution. So let's expand this and practice our math a little bit in getting there. I can rewrite this complex operator as e alpha times e to the omega I t. So that'd be alpha t e to the omega t. And furthermore, I can write e to the omega I t using Euler's equation as, I can rewrite this as cosine of omega t plus I sine of omega t. So when we do this, I can rewrite this thing as a1 e to the alpha t times cos omega t plus I sine omega t plus a2 times cos e to the alpha t. So I get cosine of a negative omega I t is just omega t. So the cosine of a negative is just cosine. But then I have to get minus, okay, the sine of omega, negative omega is a negative sine omega t. And there's an I there. Okay, we can rewrite this again. And I'll pull the cosines together and the sines together. So my cosine, I get a1 plus a2 e to the alpha t cosine omega t. And then I get my sine, so I get a1, look, minus omega 2 e to the alpha t sine omega t. And then I'm going to rename, I'm headed toward our standard form. I'm going to rename this, I'll call this A1 prime, and I'll call this thing A2 prime. So that'll allow me to rewrite this as A prime e to the alpha t cosine omega t plus A2 prime e to the alpha t sine omega t. Okay, we're almost there now. Oh, by the way, I forgot my I. My I. And then I'm going to do one more step, which is I'm going to let these are typical steps we use in trig. I mean, they're trig or kinematics, we do them. I'm going to let A1 prime equal cos phi and A2 prime equal sine phi. I can do that. You could show that I can do that. When I go about that process, oh, actually, I need to make it an A, some constant A. So you can just consider A1 prime, A1 prime, A2 prime is just terms, and I can replace them with a polar expression, A cos phi and sine phi. All right, when I do that, I can combine this thing. So I'm going to get A times e to the alpha t times cosine of phi cos omega t lost a sign somewhere. I think I put a negative sign in here. I'll put a negative because I want a negative here. Okay, did you see my negative? I pulled the negative out. Sorry, I pulled that negative out. That allows me to write this as cosine omega t. Notice I'm going to get a cosine phi cos omega t minus sine phi sine omega t. And cos phi cos omega t minus sine phi sine omega t is going to be cosine of phi plus omega t. That's what I'm after. Or omega t plus phi. And I'll rewrite this one more time. So my solution is x equals a e to the alpha t cosine of, I'll write the omega t first, omega t plus phi. So typically, this is the typical way we'll write the solution. Typical way of writing it. But just recall, this just means I had the original solution, x equals a e to the RT. I had two values for R, R1, R2. They were complex, and I plugged them back in and then did this math to work up in this format. Recall that alpha is the real part of my real part of R, basically, and R was our term in our characteristic polynomial. Omega was the imaginary part. Imaginary part of R. A comes from the initial conditions, and phi comes from the initial conditions. So we've got two initial conditions, and we get two of these terms. And when I look at this guy one more time, when I look at this, notice that A gives me my amplitude of my response. E alpha t, that's going to be an exponential term. Obviously, it's exponential. It's, we'll just write it down. It's exponential. And that means it will either decay. Under what conditions does it decay? It decays if alpha is less than 0, negative, or it will grow if alpha is greater than 0. And then we get this sinusoidal term. So cosine, that's the sinusoidal term. Just say that to be obvious. I'll just write it all out. That's a sinusoidal term. Omega is our frequency. So omega gives us the frequency of the response. And phi gives us a phase shift for the response. And it's a phase shift, I guess, from, if at time 0, it's a phase shift from time 0, I guess we could say. So at time 0, cosine at time 0 should just be 1, which means at the initial time, your x should be at the maximum amplitude. If, however, your x is not the maximum amplitude, then you've got some phase shift and it shows up there in phi. Alternatively, I mean, that's the normal way we think of it. Alternatively, you could go back up to one of these earlier expressions here and say, well, I've got, kind of this exponential part. I've got an amplitude and exponential part over two terms. Probably, though, the one below makes more sense. So that's what the phase shift means. Note if your real part, if your solution is imaginary only, then you only have damping. But this is the general solution. So let's write it. This is the general solution. Let's note that the decay case, a decaying amplitude, lambda equals 0, decaying implies typically a stable case. And alpha being greater than 0, the real part being greater than 0 implies unstable or unstable. So in dynamics, when I solve this problem, I can either see is my system stable or unstable. That's actually a big deal. So if my real part is less than 0, I'm stable. If it's greater than 0, I'm unstable. And if we look at the frequency, let's look at the frequency. So for the case of alpha less than 0, which is a stable dynamic case, if omega is 0, which seems kind of odd, that'd just be a 0 term. I've just got flat line. That's statics. If omega is not 0, then I've got oscillation. My system just oscillates. And it decays over time. So that would look, something like this. So there's my omega, and here's my alpha. For the other case of alpha, well, for the case of alpha equals 0, I just get a steady, all right, and it goes on forever. For alpha greater than 0, I get something that grows over time. And this is my alpha, and again, this is my omega. With alpha, if alpha is greater than 0, if omega equals 0, then I just get, again, a static, what we sometimes would call static instability. The term would really just follow this line. This shows up in certain problems. Sometimes it's called buckling or other things where we have static instability. If omega is not equal to 0, then we sometimes call this dynamic instability. And Moon talked about this in the book. Actually, I pulled this language from him. So we get a case of static instability. And sometimes this is called flutter. Sometimes it's called other things. Trying to think of some other things. Can't think of any right now, but you get that dynamic response. Okay. Everyone good? Feel free to call out if you have any questions or send me a chat. I'm going to take a second to look at the chat. Oh, okay. I'm looking way back at the beginning. Dropbox links are not working. Okay. Oh, in the back. Oh, sorry. I'm not watching my chat very well. So, yeah, Preston asked if it was a KX, and I went back and caught it. Luckily, Preston's Essence was there helping me. Okay. Gosh, I got to see a way to keep the chat going. Okay. Oh yeah, Preston, yes, Preston is definitely telepathic. All right, so now I realize this, I'm glad you did that, Drew. So if I keep my eye on the more, maybe there'll be some signal I'll get when a chat comes in and I can see that. Oh, or I could just leave this up. Oops, I lost it. Not sure if I can, let's see if that can flow down here, see how that works. Okay. So that's this, well, that's not quite everything. As you know, I'm never done. There's a couple things I want to add. So that's our just traditional way we treat the second order constant coefficient, homogeneous solutions. If I have a system of equations, I can do the same thing. So if now X is a matrix, and I'm going to look at just casting these as a system of first order differential equations in a state space form. So if I rewrite my problem, now my differential equation, again, I'm rewriting as a system of first order differential equations, but it's still the same idea. I can now solve this problem really in the same way. The difference is, rather than having a single term, a single characteristic polynomial, I get a system of these. And so I would set this thing up, you know, I would assume a solution and solve, and the solution becomes the solution to the eigenvalue problem. So the idea would be, we'd assume X equals A e to the lambda t. We would, oh, I'm using too many A's here. Maybe I should make that C. Actually, let me change my notation here. Let's leave that as A, and let's make this something else. Would be a good eigenvector. Let's call it V. So we assume a solution to the eigenvalue problem. We can plug it back in, or excuse me, we can plug in the solution. We can then see that gives us the eigenvalue problem with V. The V's here are the eigenvectors, and lambdas are the eigenvalues. And of course, we get these by solving the problem. Yes, and that is e to the lambda t. E to the lambda t. And the lambda are the eigenvalues. And this comes from solving the problem A minus I lambda. And the lambda is a vector. I mean, we get multiple of them. So, or we do that. I take that back, yeah. We go through each term in lambda. So let me write it like that. Maybe I should write it as lambda, yeah. Let me be a little sloppy on how I'm writing that math, but this is the problem. Okay, so you solved the eigenvalue problem. At this point, you can solve these eigenvectors and eigenvalues. It takes a little time. It's not that, I mean, it's quite a tractable problem. Much like the matrix inverse, you know, this type of thing will be pulling MATLAB to solve the eigenvalue problem for us. Again, returning eigenvalues and eigenvectors. And if you use MATLAB, make sure you review the way that it normalizes or selects and orders the eigenvalues and eigenvectors. Perhaps we ought to come up with a little tutorial on that at some point. Ask questions, though, if you get into that and try it. So that's how we deal with systems of equations, which we'll run into. And then the last thing I want to mention is, you know, I had said that we will really, for all practical purposes, we're always going to have nonlinear equations. It seems unrealistic that we'll get linear equations. However, in many of these problems, I will seek to linearize. So seek to linearize nonlinear equations. And I've got a couple useful tools to do that. You know, our big one is our Taylor series expansion. To some degree, we might say that the Taylor series expansion is the primary tool that well, it really is. It's the primary tool that we use to derive those. There's lots of good examples on Taylor series expansions. I ought to post, I have a paper I just published. It was a robotics control, mobile manipulator robotic control problem. And we derived the dynamics. They were fairly nonlinear, but we were looking at a specific problem, particular type of controls in linear form, and we use this Taylor series expansion to get to that. It's just one example. There are many examples out there. This is so commonly used. Anyhow, that's the first method. As a subset of that, Taylor series expansion shows us in many cases that we can assume, or many of the common, okay, I should say this. So let me write it like this. Taylor series expansion, that's what you want to use. Let's put a cloud around that. Now, there are many common simplifications that can be shown from that Taylor series expansion. Call this the TSE. And let me mention a few. So if you have if you can assume small angles, and by small angles, I would say sub 10 degrees, although it very much is a function of your problem, what kind of error you can tolerate. Then we say that cosine of theta can approach 1, sine of theta can approach theta, tangent of theta approaches theta. Also, for for small angles, or excuse me, another common assumption is that we'll ignore higher order terms, HOTS, higher order terms. And some of those might be commonly, if you have a derivative, a theta dot times an alpha dot, for example. Okay, so that's some velocity. Maybe I should just write some qi dot, qj dot, for example, or greater. In other words, a qi dot, qj dot, qk dot. The assumption here is that the q sub I dot is small, and all the QIs are small, dots are small. So when you square a small number, it gets quite a bit smaller. These are actually pretty good workhorses, and you can linearize most, you can linearize, really, frankly, you can linearize any dynamics problem we have if you want to live with these assumptions. The degree to which that problem is well suited to this depends on where you're looking. For example, a classical case is a pendulum. If you assume you have a pendulum motion and the angle is small, then you can make an assumption, linearize the problem. If you don't have those small motions, if you do have large motions, then these linearizations typically don't work. The Taylor series expansion, by the way, typically expands around a point in the workspace, and that's one of the advantages to it. You can linearize, you can assume small motions around a non-small angle, so you can have perturbations from some non-small angle, and that's really quite useful. I guess that would be an expansion of these using Taylor series. All right, so we've got, in general, nonlinear equations. You can linearize the equations using some of the techniques here. Once you've linearized those, you can then go back, use a closed form solution to solve the problem, come up with a solution. In the general case, you'll get two roots that are complex. The solution will be of this form, where alpha and omega are the roots. Alpha is the real part of the root, omega is the imaginary part of the root. You'll use your initial conditions to find the amplitude and the phase shift term. If alpha is negative, it means your system is stable. That's really what you're looking for in general. If alpha is positive, greater than 0, means it's unstable. If it equals 0, if you just have imaginary roots, then the system is just oscillatory. Omega indicates the the frequency of the system. The larger the value, the higher the frequency, or in other words, the shorter the period. And that's what you're looking for in dynamics. And then you can do the same thing for system of equations. But now, rather than solving a single characteristic polynomial, you've got to solve, a system of them. So it becomes this problem. You solve for the lambdas by setting the determinant of this equal to 0. So I should have written that. Equal to 0. Solve for the lambdas. Put it back in. Solve for the eigenvector. The lambdas are the eigenvalues. Solve for the eigenvectors, and that leads to your system of equations. Okay. Any other questions? I've got mine in the chat.